You know that little box that charges your phone or your laptop? We plug them in every single day, but have you ever really stopped to think about what's going on inside? It might seem simple, but it's a whole world of fascinating engineering decisions. And today, we're going to peek inside.
I mean, we've all been there, right? You get a new phone, and the charger is so small you could lose it in your pocket. But then your laptop needs this absolute brick to get the job done. What's the deal? Let's find out.
The size and shape of that little box is no accident. It's actually the result of this intense, high-stakes balancing act. An engineer has to juggle cost, size, safety, and performance, all to get power from your wall into your device. Every single charger is a totally unique solution to this puzzle.
At its heart, the biggest challenge is this. How do you take the high voltage coming out of your wall and safely turn it into the low voltage that your battery needs? Well, to do that, an engineer has a pretty specific set of tools.
And here they are, the main tools in the toolkit. You've got the buck converter, which, you guessed it, steps voltage down. The boost converter steps it up. And then you have the buck boost converter, which can go either way, up or down. Now, you're probably looking at that last one and thinking, well, that's a no-brainer, right? The perfect all-in-one solution.
And yeah, that's a perfectly logical thought. Why would you bother with two specialized tools when one multi-tool can do the whole job? But as they say in engineering, there is no such thing as a free lunch. And this is where we find our first really critical trade-off.
It turns out that all that amazing flexibility, well, it comes at a pretty steep price. There's a hidden stress factor lurking inside the buck boost converter that pushes all of its internal parts right to their breaking point. It's a much tougher tool to work with than you'd think.
And this quote from MIT professor David Perrault just nails it. Engineers aren't just drawing pretty diagrams on a computer. They have to go out and buy real physical parts that have to survive some seriously extreme conditions. And as he says, if a component gets stressed too much, it doesn't just fizzle out, it can literally blow up.
So let's look at what that stress actually means in numbers. Check this out. The components inside a buck boost converter have to handle the input voltage plus the output voltage, and at the same time, the input current plus the output current. We're talking about addition here. That forces them to be big, beefy, and expensive, because they're constantly being pushed to their absolute limits. So, if the all-in-one multi-tool is just under way too much stress, what's the alternative? Well, we go back to our specialists, the good old buck and boost converters. They might not be as flexible, but, as we're about to see, they have a massive advantage when it comes to handling stress. And this, right here, is the absolute game changer. While the buck boost has to handle the sum of the voltages and currents, adding them together, our specialists only have to handle the maximum of the two, just whichever one is bigger. And let me tell you, going from sum to max is a world of difference in engineering. It means designers can use smaller, cheaper, and way more efficient parts. So, why the big difference? Well, think of it this way. The buck boost converter is like a middleman. It takes all the energy from the input, holds onto it for a second, and then gives it to the output. The specialists are much, much smarter. They let most of the energy flow directly from input to output, and they only touch the small amount of energy they need to adjust the voltage. Less handling means way less stress. Okay, so we've picked our less stressed specialist converter. We're feeling pretty good. Problem solved, right? Not quite. Now we run smack into the next layer of the challenge, actually building this thing in the real world. See, up till now, we've been operating in a theoretical paradise. We've just assumed we have access to perfect, infinitely large components that can store and release energy with perfect smoothness.
But of course, you can't go to the electronics store and ask for an infinitely large capacitor, right? You have to use real parts that fit inside that tiny plastic case. So what happens when we're forced to use smaller, real-world parts?
What you get is something called ripple. Because those internal parts can't store and release energy perfectly, the power coming out isn't a perfectly flat, smooth line. Instead, it's got these tiny, unavoidable, wave-like fluctuations in it. The entire goal of the designer is to make that ripple as small as humanly possible. So how do they do it? It's actually a pretty straightforward recipe. First, the engineer decides exactly how much ripple is okay for the device they're powering. Then, they plug that limit into a special design formula. And finally, that formula spits out the exact size of the components, the capacitors and inductors that they need to buy. And this calculation, this simple formula, brings us right to the heart of the matter. This is the fundamental trade-off that every single power electronics designer faces, every single day. Here's the first big trade-off. If you want incredibly clean, stable power with almost no ripple, you can have it. But you're going to need larger, bulkier, and more expensive components. If, on the other hand, the device can tolerate a little bit more ripple, you can get away with using much smaller, cheaper parts. It's a classic seesaw.
But designers have a really clever trick up their sleeve to get around this: switching speed. Imagine you're trying to fill a bucket that has a tiny leak. If you pour in water slowly, say once a minute, you need a huge bucket to keep the level from dropping too much. But what if you could add a tiny drop of water millions of times a second? You could keep the level perfectly steady with a teeny tiny bucket. It's the exact same idea here. By switching the power on and off at insane speeds, designers can get low ripple with much, much smaller components. This is the secret sauce behind today's tiny, powerful chargers.
So in the end, it really is this complex balancing act. The designer is constantly trading off performance against physical size, and both of those against cost and how efficient the whole thing is. Every single power adapter you own is just one engineer's unique answer to that four-way puzzle.
So the next time you plug in your phone, just take a second to look at that charger. It's not just a boring plastic box, is it? It's a tiny marvel of engineering compromise. And now you can ask the right questions. To get it this small, did they crank up the switching speed? Did they choose a less stressed specialist converter? You now understand the hidden language of trade-offs that engineers use to design our world.